Earth, a unique planet, restless and dynamic. Continents shift and clash. Volcanoes erupt. Glaciers grow and recede. Titanic forces that are constantly at work, leaving a trail of geological mysteries behind. This episode travels back in time to investigate the greatest geological mystery of all, the birth of the Earth. Scientists explore how our planet first formed from the dust of the solar system, how molten rock solidified to land, how our oceans filled with water, and how life arrived on Earth. These are the earliest chapters in the incredible story of how the Earth was made. When it comes to finding clues to the birth of the Earth, our planet has been good at covering its tracks. Billions of years of erosion, volcanic activity, and the shifting of continents and oceans have destroyed almost all the evidence of the earliest stages in Earth's formation. For geologists trying to discover how and when the Earth first formed, this is a major challenge.
As geologists began to question the age of the Earth, and of course they looked for older and older rocks, what we began to find was that the further back you go in Earth history, the harder it is to find any of those rocks.
The search for the oldest rocks on Earth brings investigators to the harsh desert landscape of northern Arizona. This giant hole in the ground is Meteor Crater, formed when a massive meteorite slammed into the Earth.
We didn't really have rocks from the very beginning. Well, where could we find something? What about the meteorites that have been out in space and fall on the Earth?
It was here that geologists made a vital discovery. Meteorites are older than any rocks on Earth. They had found the key that would unlock the secret of Earth's formation. If the oldest rocks came from space, that is where the investigation must begin, in space. Our solar system, 4.5 billion years ago. At its center, the young sun.
The theory that emerged was that the sun was surrounded by a cloud of dust and gas, and as that cloud cooled, little grains of minerals formed. So all these little grains of minerals floating in this gaseous cloud are moving around the sun, and they start to bump into each other.
But there was a problem with this theory. Nobody could explain how colliding microscopic mineral grains could ever create an object the size of a planet. Then, in 2003, an experiment on board the International Space Station accidentally provided extraordinary new evidence. Astronaut Don Pettit wanted to see what happened to different substances in the zero-gravity conditions of space. He did a simple experiment by pouring some salt into a plastic bag and shaking it. The results were astounding. The particles immediately began to stick to each other, forming little clumps, all held together by tiny static electric charges. Scientists realized that if grains of salt stuck together in space, then so could the mineral grains in the solar dust cloud. Here was real evidence for the fundamental mechanism that kick-started the formation of the Earth. As mineral grains in the solar dust cloud bumped into each other and stuck together, they grew into small pieces of rock orbiting the sun. Over the next few million years, some of them collided and grew bigger. Many of these rocks are still orbiting the sun today. they have drifted for the past 4.5 billion years, unchanged from when they first formed. Occasionally, they fall to Earth, and we call them meteorites. They provide scientists with an incredible window onto the past.
We brought what's called a stony type of meteorite. What the scientists do then is slice across it and look on the inside. And to a planetary mineralogist, you start seeing all kinds of wonderful things.
This meteorite contains minerals and metals from every part of the solar dust cloud.
So what we're looking at is the assemblage of all these little ancient materials that were floating around the sun in the nebula of dust and gas. And when they hit each other, they gradually aggregated into solid bodies, which got bigger and bigger.
Gradually, billions of these rocks grew as they orbited the sun. First to the size of boulders, then as big as houses, and they kept on growing. When an object reached about half a mile across, its own gravitational pull became strong enough to draw other objects towards it.
Some object in this huge number of objects going around the sun, one of them had to be the biggest. And as soon as it gets bigger than the others, it's sweeping up more objects, just like you're driving through a cloud of mosquitoes at night in your car and the front windshield's getting hit more often. So the bigger it is, the faster it grows. And the faster it grows, the more gravity it gets, and that pulls in more objects. So the biggest object starts to run away from the crowd. It starts to grow fastest.
Is separated into distinct layers, a thin crust, then a massive dense layer of rock called the mantle, and at the center, an iron and nickel core. Some extraordinary event must have occurred to transform the interior of the young planet. Geologists now believe that soon after it formed, the Earth completely melted.
Originally, the Earth was probably just a big collection of rocks like this, but it heated up to the point where these rocks all melted. And when that happened, the denser elements sank down through to the very core of the Earth, and the lighter elements floated at the top.
The huge gravitational pull dragged the heavy iron and nickel down to form the core and separated the rest of the planet into layers. What caused such a huge mass of rock and metal to heat up in the freezing depths of space puzzled geologists for many years.
We think it's from the incorporation of very hot radioactive elements. They're out there floating in space. As the Earth accretes, it includes some of this ferociously hot material. As it gets inside there, it begins to heat up the rocks around it. And if you build the Earth fast enough and you incorporate enough of this really hot radioactive elements, it'll be enough to melt the Earth from the inside out.
Only 30 million years after it began to form, Earth had become a giant round ball of boiling liquid rock and metal orbiting the sun.
Imagine a totally molten world. I mean, it had molten magma oceans, no dry land anywhere, no water, just flowing lava everywhere.
The temperature of the molten Earth was now a staggering 2,000 degrees. But at the edge of the planet, the vacuum of space is a constant minus 450 degrees, almost 2,500 degrees colder. The surface rock could not stay molten for long.
It's cooling from the outside in. So from the outside begins to crust over, and you get this little scab, like on a wound, of cooled rock, but still really hot, and then gradually begins to cool from the outside in.
In less than 1 million years, Earth's surface was covered in a thin crust. But volcanoes still spewed out lava and choking gases. Meteorites rained down in a constant bombardment. Earth had a long way to go before it could support continents, oceans, and life. Scientists investigating the earliest origins of the Earth have uncovered evidence from salt grains in space. They revealed that the Earth began to form when fragments of the solar dust clouds stuck together. The Earth's internal layers provide the clue that soon after it formed, the young planet completely melted. Scientists had worked out how the Earth first formed from a cloud of dust in space, but they were missing a vital piece of the puzzle. They still did not know the age of the Earth. Billions of years before humans evolved, tiny mineral grains in space clumped together to form the molten ball that became the Earth. But exactly when that happened is a question that has taxed the minds of scholars and scientists for centuries. In 1650, the Irish Archbishop James Ussher added up the ages of all the prophets and kings in the Bible. His calculations led him to very precise conclusions. That Earth was created at nightfall before Sunday, October 23rd, 4004 BC. A century later, geologists realized that Earth's thick layers of sediments and volcanic lavas must have been laid down over millions, rather than thousands of years. The next breakthrough came in 1897, when physicist Ernest Rutherford figured out that measuring radioactive decay could accurately date the age of rocks. Rock samples from around the globe were found to be not just millions, but billions of years old. But in their hunt for the age of the Earth, scientists hit a major obstacle. Rocks from the earliest stages in Earth history are very hard to find.
If you want to go back as a geologist and try to find evidence of those early days, it's very hard to do on the Earth because, of course, we have rain eroding, we have tectonics and continental drift destroying continental surfaces. We simply can't find the rocks that go back to that age.
In the early 1950s, the American geologist C.C. Patterson tried a new approach, using meteorites. He knew that meteorites must have clumped together from the same mineral grains in space that formed the Earth. And that happened at the same time as the Earth was born. So if he could date a meteorite, he should get the true age of the Earth. In 1953, Patterson came to Meteor Crater in Arizona, looking for samples. The meteorite which blasted out this enormous crater was about 50 yards across. It slammed into the Earth at a fantastic speed.
Objects hitting the Earth from space may typically come in at 10 or 15 miles per second, hitting the ground, penetrating into the ground, generating an enormous pressure and shock wave and creating a huge explosion.
The meteorite hit the Earth with the force of a 2-megaton atomic bomb. The explosion vaporized most of the meteorite, but individual fragments survived.
This is one of the pieces of the object that crashed into the Earth and made this crater. This is pure iron. We know it's iron because, for example, it's magnetic. An amazing piece of something that was floating in space. This was the kind of place that people could get samples for the first radiometric dating of meteorites. And so Patterson came here and got samples like this.
Patterson dated the samples and was amazed by the results. The meteorite was a staggering 4.5 billion years old, meaning that the Earth was also born 4.5 billion years ago. Patterson had solved the problem that had defeated scientists for centuries.
There's this apocryphal story that Patterson got so excited about the date that was coming back from the laboratory and so hyper about it, he thought he was having a heart attack. And he was driven to the hospital, and it turned out to be just his excitement over this fantastic discovery.
Modern radiometric dating techniques have refined the age of the Earth to a remarkable degree of accuracy. The most recent study dates the Earth as 4,567,000,000 years old. So scientists now knew how and when the Earth was formed, but nobody had figured out what happened next. Then in 1974, a radical new theory emerged. In the early solar system, there were dozens of mini-planets chaotically orbiting the sun. According to the theory, one of these was on a collision course with Earth. The idea was the brainchild of Bill Hartmann, who was trying to explain the origin not of the Earth, but of the Moon.
What we came up with was that maybe during that period of intense impacts, maybe very large impact hit the Earth and blew some crustal outer mantle rock off of the Earth into space around the Earth, and the Moon formed from that material.
Hartmann suggested that another planet, about the size of Mars, crashed into the Earth. He claimed that the Moon could have been formed by debris from that collision. To many scientists, this was nothing but fantasy, but Hartmann had evidence. Collected from the Moon itself.
I fall into plumb crater getting this rock.
Footage from the Apollo 16 mission in April 1972 shows astronaut Charles Duke struggling to pick up a large sample of moon rock to bring back to Earth for geologists to analyze.
That's 20 pounds of rock.
At the Johnson Space Center in Houston, this actual piece of moon rock is still kept under strict laboratory conditions.
I would say, behold the Moon. This is an actual piece of the Moon, and it's the largest single rock that they brought back from the surface of the Moon when the Apollo astronauts went there. We can't touch it. They don't want human beings touching these rocks and leaving organic material on them.
Until the late 1960s, geologists thought that the Moon formed in the same way as the Earth, by clumps of mineral grains sticking together in the solar dust cloud. They believed it had layers, like the Earth, and a heavy iron core. But when geologists analyzed lunar samples, they were astonished to discover that the moon rocks contained much less iron than they expected.
One of the mysteries has always been, why isn't there as much iron in the Moon as there is on the Earth if the two objects are right close together in space?
The question bothered Hartmann so much that he began to think that conventional theories about how the Moon formed might be wrong.
That lack of iron in the Moon, or to put it another way, the fact that the Moon is made out of rock that looks like the crust and the upper mantle material of the Earth, that was a clue that the Moon may have formed from rocks from the outer portion of the Earth.
This was the key to Hartmann's idea of a collision between Earth and another planet. The force of the impact completely destroyed the other planet and flung billions of tons of Earth's crust and mantle out into space and into orbit around the Earth. Within a few thousand years, this debris clumped together to form the Moon. Advanced computer models showed that the collision was a glancing blow. The other planet did not hit Earth head-on. This meant that while Earth's outer layers were ripped off, none of its iron core was blasted away.
That lack of iron would end up explaining why we have a Moon that is only the rocky material without the iron material.
Hartmann's collision idea is now accepted as fact. It was his fascination with the Moon that led to a new understanding about a vital stage in the formation of the Earth.
The moon always, to me, is a reminder that we live in a larger environment than just the Earth. It's the cosmic environment. The inner solar system is our environment that we can move around in now.
In the quest to discover the age of the Earth, evidence from radiometric dating of meteorites proves that the Earth was formed just over 4.5 billion years ago. The lack of iron in rocks brought back from the moon is evidence that the Earth survived a massive collision with another planet. But vital parts of the modern Earth were still missing from the newly born planet. The investigation now needs to figure out how the Earth gained two essential components: solid land and water. $4.5 billion years ago, Earth formed out of the solar dust cloud, then survived a devastating impact with another planet. The investigation now moves 200 million years forward in time as scientists try to discover how the first continents and oceans formed. They are looking for evidence on the northeast shores of Hudson Bay, Canada. This is the desolate landscape of Porpoise Cove, the site of an important new scientific discovery. And it's all down to a young PhD student's fascination with ancient rocks.
I was interested in studying the early Earth, so the idea is to get as far as we can back in time to get these old rocks and study rocks that were there in the past.
Geologists already knew that rocks in this part of northern Canada are extremely old. But something about a small area in this vast wilderness caught O'Neill's eye.
The overall aspect of the rocks really looked different. And right away we knew that something was really bizarre, really unusual about these rocks.
The rocks are highly altered, deformed volcanic lavas known as amphibolites.
The chemistry was unusual, the mineralogy was unusual, and nobody had seen rocks like that before.
O'Neill decided the rocks needed further investigation. He sent samples to be radiometrically dated. The results were astounding.
We were in the lab in Washington, D.C. when we first got the first number out of the machine. And the first reaction is we didn't believe it. So what you do is you reanalyze the rock a second time. And then the same number comes up, and then a third time, and then again and again. So you say, okay, we'll analyze more of these rocks because I can't believe it. And these numbers, the signature, this really, really old signature keep coming up, keep coming up, and keep coming up. And in the end, you have to come to the conclusion that these rocks have been formed nearly 4.3 billion years ago.
The results were indisputable. The amphibolites are 4.28 billion years old, 200 million years older than any other rocks so far discovered. They are the closest anyone has come to finding Earth's original crust.
These are the oldest rocks in the world, and it's amazing when you stand on it. You can try to imagine yourself almost 4.3 billion years ago when the Earth was so young and just barely forming. Walking on this landscape. And it's a really amazing feeling.
These rocks are now yielding clues about the thickness of the early crust. O'Neill has found unusual minerals which can only form in conditions of very high temperature and pressure. They prove that the amphibolites were made at least 12 miles down in the crust of the Earth. This means that more than 4 billion years ago, Earth had a solid crust at least 12 miles thick. And a crust that thick suggests there must have been continents. And there's more. Evidence hidden in the amphibolites reveals that these rocks must have originally formed deep underwater.
Well, you have to understand that when rocks form, they can record their chemical signature. And depending on where the rocks are formed and what geological context they will be formed, they will carry that specific chemical signature.
The chemical signature of the amphibolites is unique. It proves that when these rocks formed, Earth had not only a solid crust, but oceans.
The signature we see here, it really looks like an oceanic floor. That means there was an ocean and a lot of water already at 4.28 billion years old. So it totally changes our view of what the Earth was like before.
To the scientific world, this idea is dynamite. But O'Neill is not on his own. There is more evidence to back up his claim. In the same ancient rock sequence, geologists find another unexpected rock type called banded iron formations. These rocks are made up of alternating light layers of silica and dark bands full of a mineral called magnetite, which, as the name suggests, are rich in iron.
We usually use a magnet to try to find these minerals. It's a quick and easy way to identify for sure those rocks as banded iron formation.
Magnetite in banded iron formations only forms underwater. So these rocks are further evidence that there were oceans on Earth more than 4 billion years ago. But scientists don't know how much of Earth's surface was covered by water.
The only way to form this magnetite is to be like in an ocean. We don't know exactly what was the ocean at that time, but we know for sure that we need water to form those rocks.
These discoveries are forcing geologists to rethink their ideas of what conditions were like on Earth less than 300 million years after the planet formed.
People often think of this earlier like a ball of fire, a molten rock, but this is not the picture that we see here. We see that already at 4.28 billion years old, we probably had an ocean. We had continent that really, really looks like what we know today. So it changes totally our view of the early Earth.
The investigation has now revealed when the Earth's continents and oceans began to form. Evidence from amphibolite rocks at Porpoise Cove confirms that the Earth had developed a thick, solid crust 4.28 billion years ago. Banded iron formations in the same rocks show that there were oceans on Earth's surface at the same time. All of which raises another mystery. If oceans existed more than 4 billion years ago, the investigation needs to figure out where all the water came from. After its formation from the solar dust cloud 4.5 billion years ago, Earth was a fiery ball of molten rock. But 200 million years later, the first oceans were already forming. And Earth today is the blue planet, with 70% of its surface covered by water. The investigation now looks at the mystery of the origin of Earth's water.
One of the important questions I've always thought about is, where did all of this come from? All of this water, all the water in the oceans and in the atmosphere, in our bodies, in the ground. When you look at the Earth from space, what really impresses you is the water, how beautiful this planet is. Why does Earth have all this water? And how did it get here?
The question has puzzled geologists for years. Now, they believe the answer lies in space. New evidence showing how our water arrived on Earth has emerged from a meteorite that fell in 1998, but which has only recently been analyzed.
We found an astonishing thing. This meteorite contains grains of table salt, just like you put on your fish and chips.
The clue is trapped inside the crystals of salt and revealed under the microscope. Minute droplets of liquid water.
On the computer screen, you can see a little fluid inclusion, a little drop of water, And you'll know it's water. We know it's liquid because you see a little bubble moving around inside of this little droplet of water.
The amazing thing about this discovery is the age of the water.
You can date this by several different dating techniques. The salt itself is 4.5 billion years old. The water inside has to be at least that old, if not even older. There's no question about it. And so this water is at least as old as the solar system.
Here is visible evidence that water existed in space when the Earth first formed. And Zelensky is convinced that meteorites then brought the water to Earth.
And so it's looking more and more like the water arrived drop by drop in rocks like this meteorite here, landing over the course of billions of years. You have lots of material coming in every day and smacking into the Earth and depositing a little bit of water, a few drops at a time.
The scale of the meteorite bombardment needed to fill the oceans with water is almost impossible to comprehend. But scientists believe that over billions of years, there were easily enough meteorites crashing into the Earth to account for all the water on the planet.
Gradually, those rocks are sweating water, building up first shallow seas here and there that grow to be giant oceans. We go from this to this.
Once Earth had land masses and water, the stage was set for the development of life. The next phase in the evolution of the Earth. Life is an essential element in Earth's geology. Without life, sedimentary rocks like chalk and limestone would not exist. Without life, there would be no coal, oil, or gas. Life has shaped the Earth in profound ways. But finding the origin of life has challenged scientists for hundreds of years. Now there's a new explanation. It comes from evidence found at Allende in the desert landscape of northern Mexico. At about 1 a.m. on February 8, 1969, night suddenly turned into day.
A large fireball was seen travelling from the south northwards over northern Mexico. And this big flash and this fireball was caused by a really large meteorite. It was probably about the size of a car, and it entered the top of the Earth's atmosphere at about 36,000 miles an hour.
As it plunged through the atmosphere, the meteorite broke up into thousands of fragments.
There was no crater left by the Allende meteorite, so it fell as a shower of stones, the largest of which was reported to be about the size of a beach ball. The stones are found in, we call it a strewn field, and it's an area about 30 miles by 5 miles wide, and we're here right in the middle of that strewn field.
Because the meteorite fragmented into so many pieces, geologists had to search a huge area to find samples.
Now, I actually have a smaller one of the stones here. You can see it's about the size of a plum. It's one of the most primitive type of meteorites. This means that since it formed at the very earliest stages of solar system formation, really not much has happened to it.
When they analyzed samples from Allende, geologists made a groundbreaking discovery. The meteorite contained tiny amounts of chemicals called amino acids.
Amino acids are terribly important constituents of things like proteins, and amino acids really are sort of like the chemical building blocks for life. So to find these amino acids, these molecules within the meteorite, was a really exciting discovery.
Every living thing on Earth, plant or animal, contains amino acids, and life could not exist without them. Until they were found in the Allende meteorite, scientists believed that amino acids were first made by chemical reactions on the surface of the Earth.
People thought that maybe life had started on Earth in these sorts of warm pools, maybe, a few 100 million years after Earth actually formed, or possibly through lightning causing chemical reactions in the early atmosphere. There was a few theories as to how life may have started on Earth prior to the discovery of amino acids in meteorites.
Since Allende, amino acids have been found in hundreds of other meteorites. Their discovery has revolutionized ideas about the origin of life on Earth. Scientists now believe that the building blocks of life originally came from space. Meteorites containing amino acids have bombarded Earth ever since the planet formed, and it was these amino acids which were the starting point for all life. Hunting for the origin of Earth's water and life, the investigation has revealed that the water on Earth arrived here inside meteorites. And meteorites also brought amino acids, the building blocks of life, to Earth from space. Scientists now need one more piece of the puzzle to explain the final stage in Earth's journey. From particles in the solar dust cloud to a planet where life itself builds Earth's geological features. $4.5 billion years ago, Earth formed out of the solar dust cloud. 200 million years later, the first continents and oceans were developing. Meteorites brought water and amino acids, the building blocks of life, to the surface of the planet. The investigation now moves forward to the period 3.5 billion years ago. New forms of life were about to emerge, which by their very existence would create new kinds of rocks. But life as we know it needs oxygen, and 3.5 billion years ago there was no oxygen on Earth. At the time, the atmosphere was deadly poisonous. Volcanic eruptions filled the air with a choking mixture of sulfur, methane, carbon dioxide, and sulfuric acid. But primitive life forms did exist. The fossilized remains of strange coral-like structures have been found in rocks more than 3 billion years old in many parts of the world. They are called stromatolites, and they are a clue as to how the atmosphere filled with oxygen. Living stromatolites are incredibly rare. One of the few places on Earth where they can be found is in another part of the northern Mexican desert. This is the high valley of Cuatro Ciénegas.
You might think that this is just any old desert, but it's not. This is a very special place because of particular way the chemistry is in this valley. It's unlike any other place on the planet.
The pool is like a time capsule laboratory. By examining the modern stromatolites, scientists can work out how they were made more than 3 billion years ago.
What's interesting about Cuatro Ciénegas is that this is almost like a proxy to right before the world had a lot of oxygen in it. And the place was dominated, our Earth was dominated by microbial life.
Seifert has discovered that the stromatolites are made by billions of microbes called cyanobacteria.
These right here are the stromatolites that are here at Cuatro Ciénegas. I have a piece of it here, and if you can see this blue-green rim right here, this is millions and millions of cyanobacteria.
These bacteria were to change the course of Earth history because of one unique feature. They produce oxygen.
Here at this pond, we can actually see them doing their job. We can see them making that oxygen. So when I get in the water and I actually go up to one of these cyanobacterial mats, if I look very closely, all of the community is making oxygen. And as that oxygen collects in that mat, it produces a little air bubble. And you can watch that air bubble just transfer to the top, and that's actually when oxygen is being released to the atmosphere.
$3.5 billion years ago, oxygen was deadly poisonous to other early life forms, which used sulfur to obtain energy.
Cyanobacteria developed a little molecular machine that could actually take sunlight and take water, and they made a byproduct that was oxygen. Well, on this planet back then, none of the life was used to oxygen. And it's at that point in life's history when they began making excess oxygen that got into the atmosphere, our whole world changed in the way it worked.
Over geological time, there were enough cyanobacteria to produce trillions of tons of oxygen, creating the atmosphere we breathe today. And they were responsible for changing the way all life evolved.
From an evolutionary standpoint on planet Earth, we are where we are because of cyanobacteria and the fact that they managed to fill our atmosphere full of oxygen. Because unless we'd had that gas, we wouldn't have the complex organisms that we have on the planet. You and I wouldn't be here today.
Once the atmosphere began filling with oxygen, the stage was set for the evolution of all plant and animal life. The impact on Earth's geology was profound. Over hundreds of millions of years, decaying plant matter from tropical forests built up compressed layers, which eventually formed all the coal, oil, and gas deposits on the planet. Sedimentary rocks like limestone and chalk are made largely from the skeletons of marine animals which accumulated at the bottom of shallow seas. Without life, Earth's geology would be very different. The investigation into the birth of the Earth has uncovered evidence revealing the secrets of Earth's development. Experiments on salt crystals in space reveal that the Earth began to form when mineral grains in the solar dust clouds stuck together. Evidence from meteorites proves that Earth first formed 4.567 billion years ago. The oldest rocks in the world are evidence that continents and oceans were forming 4.28 billion years ago, much earlier than previously thought. Liquid water in meteorites proves that water was brought to Earth during billions of years of meteorite bombardment. 3.5 billion years ago, a billion years after it first began to grow out of the solar dust cloud, Earth had continents, oceans, primitive life forms, and oxygen. Earth, a unique planet, restless and dynamic. Continents shift and clash. Volcanoes erupt. Glaciers grow and recede. Titanic forces that are constantly at work, leaving a trail of geological mysteries behind. This episode travels back in time to investigate the greatest geological mystery of all, the birth of the Earth. Scientists explore how our planet first formed from the dust of the solar system, how molten rock solidified to land, how our oceans filled with water, and how life arrived on Earth. These are the earliest chapters in the incredible story of how the Earth was made. When it comes to finding clues to the birth of the Earth, our planet has been good at covering its tracks. Billions of years of erosion, volcanic activity, and the shifting of continents and oceans have destroyed almost all the evidence of the earliest stages in Earth's formation. For geologists trying to discover how and when the Earth first formed, this is a major challenge.
As geologists began to question the age of the Earth, and of course they looked for older and older rocks, what we began to find was that the further back you go in Earth history, the harder it is to find any of those rocks.
The search for the oldest rocks on Earth brings investigators to the harsh desert landscape of northern Arizona. This giant hole in the ground is Meteor Crater, formed when a massive meteorite slammed into the Earth.
We didn't really have rocks from the very beginning. Well, where could we find something? What about the meteorites that have been out in space and fall on the Earth?
Over the next few million years, some of them collided and grew bigger. Many of these rocks are still orbiting the Sun today. They have drifted for the past 4.5 billion years, unchanged from when they first formed. Occasionally, they fall to Earth, and we call them meteorites. They provide scientists with an incredible window onto the past.
We brought what's called a stony type of meteorite. What the scientists do then is slice across it and look on the inside. And to a planetary mineralogist, you start seeing all kinds of wonderful things.
This meteorite contains minerals and metals from every part of the solar dust cloud.
So what we're looking at is the assemblage of all these little ancient materials that were floating around the sun in the nebula of dust and gas. And when they hit each other, they gradually aggregated into solid bodies, which...
It was here that geologists made a vital discovery. Meteorites are older than any rocks on Earth. They had found the key that would unlock the secret of Earth's formation. If the oldest rocks came from space, that is where the investigation must begin, in space. Our solar system, 4.5 billion years ago. At its center, the young sun.
The theory that emerged was that the sun was surrounded by a cloud of dust and gas, and as that cloud cooled, little grains of minerals formed. So all these little grains of minerals floating in this gaseous cloud are moving around the sun, and they start to bump into each other.
But there was a problem with this theory. Nobody could explain how colliding microscopic mineral grains could ever create an object the size of a planet. Then, in 2003, an experiment on board the International Space Station accidentally provided extraordinary new evidence. Astronaut Don Pettit wanted to see what happened to different substances in the zero-gravity conditions of space. He did a simple experiment by pouring some salt into a plastic bag and shaking it. The results were astounding. The particles immediately began to stick to each other, forming little clumps, all held together by tiny static electric charges. Scientists realized that if grains of salt stuck together in space, then so could the mineral grains in the solar dust cloud. Here was real evidence for the fundamental mechanism that kick-started the formation of the Earth. As mineral grains in the solar dust cloud bumped into each other and stuck together, they grew into small pieces of rock orbiting the sun.